Often we will need to choose coordinate systems to specify spatial information and to help us represent vector physical quantities. We will start by using Cartesian coordinate systems, where coordinate axes are placed perpendicularly to one another, one for each dimension. Note here, dimension refers to spatial dimension, not dimensions in terms of quantities like mass, length, and time. We will run into instances where the same word has multiple meanings, so we'll need to pay attention to the usage of such words in context to be sure to have the appropriate meaning in mind. Here we're going to focus mostly on using Cartesian coordinates along a straight line, one spatial dimension. We'll say a little something about additional spatial dimensions here, but we'll save most of that discussion for later. Choices must be made up front before we can use a Cartesian coordinate system. We need to specify the origin of our coordinate system. We need to decide the axis orientation, including deciding the positive and negative directions along each axis. We need to choose a good set of units for the situation we're studying. Finally, we are free to label the axis as we like, either using standard labels or something else that is appropriate. The bottom line here is that we want to make good choices that are suited to the problem at hand. For example, if we want to describe the motion of an object that moves along a straight line, we can use a single coordinate axis to describe fully that motion, provided we choose to orient our axis parallel to the motion. Earlier we discussed representing vectors with arrows and with symbols. There's yet another way to represent vectors, once we have made a particular choice of coordinate system. It's customary to associate the positive direction of a coordinate axis with a unit vector. For each standard axis label, there is a special axis unit vector that points in the positive direction along that axis. Let's remember that a unit vector only communicates direction. The unit vector has a magnitude of 1 with no dimensions. This means we can use this axis unit vector to convey the direction information of any vector physical quantity we like. For the 1D case we're considering here, there are only two choices for the direction: the positive direction or the negative direction along the axis. As a first example, let's consider the position vector, which we can use to locate an object with respect to the origin of our coordinate system. Recall, we can always write a vector as a product of its magnitude and its direction. If the position vector points in the positive direction, the direction of the position vector is given by the axis unit vector. The magnitude is, as usual, the size of the quantity in the appropriate units. If the position vector points along the negative direction, then we can use a flipped version of the axis unit vector to represent the direction. We can take the product of this flipped axis unit vector with the magnitude of the position vector to represent the full position vector. If we rearrange these expressions so that the axis unit vector is separated from everything else, then we obtain the component representation of the vector. We need to take care to remember that a vector component is not the same as a magnitude. The magnitude never carries any direction information, but the component carries some direction information, the sign, plus or minus, along a particular axis. We'll see later these ideas are important in more than one spatial dimension. However, we do need to mention here one more thing that touches upon multiple spatial dimensions. For Cartesian coordinates, vectors can be represented in component form as an ordered triple, where, customarily, the component associated with the x-axis occupies the first position, the component along the y-axis occupies the second position, and the component along the z-axis occupies the third position. Here, since we're dealing with one dimension, once we have labeled our axis, we can set the other components to 0. So, for our two position vector examples here, we show two common ways to write the vectors in component form. Finally, we mention here that symbols are used for components, typically Roman letters, often with subscripts. Be careful though. The symbols used for components and magnitudes can sometimes appear to be quite similar to one another, so pay attention to the context in which the symbols are used. One helpful hint is that when you are writing symbols yourself, you can practice using consistently the absolute value bars for magnitudes to clearly distinguish magnitudes from components. Here's a question for you. Which of the following is the best component representation of position vector R3? The answer is D. Since we chose Z as the label for our axis, the non-zero component describing R3 should be placed in the third position when we write R3 using ordered triple notation. As we show here, we can also write R3 using the symbol for k hat, the special unit vector that always points in the plus direction along the z-axis. Here are some key points to keep in mind. There are a variety of ways the arrow representation of a vector may be placed in a coordinate system. For example, while it's natural to think of a position vector arrow with its tail starting at the origin, we're not stuck with that. We can move the arrow representing the vector around without changing either the vector itself or the vector's representations in arrow or in component form. Let's make sure we don't fall into the trap thinking that the component representation must specify where the tip of the arrow should be located in the coordinate system. This is generally not true for position vectors or any other vector quantities. The coordinate system choices we make don't change the vector. However, if we change the coordinate system, the component representation generally also changes. For example, let's say we change to a new coordinate system where we flip the axis directions. The vector and its arrow representation don't change, but the component representation does. We'll see later something similar happens in more than one spatial dimension. One more point worth mentioning arises when we use components to represent vectors whose dimensions are something other than a length. The choice of a particular coordinate system determines the directions used by all vector quantities that are expressed in component form associated with that coordinate system. However, we need to be careful not to fall into the trap thinking that the numbering on the axes is the same as the numbers that may appear in specifying the components of a vector. If the vector has dimensions other than length, then the components and the axis numbers can't be the same because they don't have the same dimensions. Question: which of the arrows shown can represent the force F2? Answer: all of the arrows shown would work. The component form of F2 tells us that F2 only has one non-zero component, which points in the plus z direction. All the arrows show this correctly. How long to draw the arrows depends on us to decide how long to draw the arrow to represent the magnitude of F2. We can do vector math with the vectors in component form. To multiply or divide a vector by a scalar, we multiply or divide all the components by the same scalar. Note that if the scalar has units, the result of the multiplication or division is a new vector with different units. To add or to subtract vectors, we add or subtract the corresponding components. We need to take care that all vectors that are being added or subtracted have the same dimensions, and that the same coordinate system was used to construct the component representations of each vector that is being added or subtracted. Question: with vectors R1, R2, and R3 given as shown, find R1 minus R2 plus R3. Here is the answer, where the key point to keep in mind is that when we have vectors in component form, we carry out the addition and subtraction separately for each component.